The title of my presentation is Spatial Segmentation of Glottal Area in High-Speed Videoendoscopy During Connected Speech. We would like to acknowledge the support provided by the National Institutes of Health. In this slide, we are gonna go over a brief background about our research. Voice disorders revealed in communication during connected speech. Although videostroboscopy is used in connected speech, it doesn't really provide details of the intracycle vibratory characteristics of the vocal folds. In contrast, laryngeal high-speed videoendoscopy, or HSV, overcomes this limitation, and it captures the true vibrations of the vocal folds during running speech. Although HSV is a powerful tool, it's not feasible to visually navigate through this huge amount of data obtained by HSV. Therefore, it's critical to develop automated techniques for analysis of vocal fold vibration using HSV. To develop an automated method for the analysis of vocal fold vibration in connected speech using HSV, we need to develop HSV-based measures of vocal fold vibration. To do so, we need to extract the glottal area waveform. Toward that goal, we previously developed a temporal segmentation and a motion compensation technique to extract HSV vocalizations and account for laryngeal maneuvers during connected speech. Spatial segmentation of the glottal area is needed to do an accurate measurement of glottal area waveform. Several approaches have been developed for spatial segmentation of the glottal area in HSV. However, the existing studies were performed on HSV data during sustained vowel production, not connected speech. The spatial segmentation of the glottal area during running speech is more challenging due to excessive laryngeal tissue maneuvers. The goal in this project is to develop a spatial segmentation method for glottal area waveform measurements in running speech based on our previously developed HSV analysis methods. The main objective of this study is to develop an automated algorithm to perform spatial segmentation of the glottal area to measure glottal area waveform in HSV during connected speech. To do so, we are using the algorithms developed previously for temporal segmentation and motion compensation in HSV in connected speech. Using these algorithms, we extract the vocalized segments of HSV recording and align the vibrating vocal folds across the frames during each vocalization. To perform spatial segmentation, we first extract the HSV kymograms at different cross-sections of the vocal folds. We then apply an active contour modeling approach to describe the vocal fold edges analytically in the kymograms. After registering the glottal edges in the kymograms back to the HSV frames, we measure the glottal area waveform for each vocalization. In this study, we use HSV data from a female participant with no history of voice disorder, and a custom-built HSV system was used for data acquisition. The participant was recorded during the production of Rainbow Passage with 4,000 frames per second and recording length of around 29 seconds. Firstly, the temporal segmentation algorithm we previously developed is used to automatically extract timestamps of the vocalized segments of the HSV recording. Then, a denoising algorithm along with a motion compensation technique are applied. These algorithms are used to locate the vibrating vocal folds in a motion window. Capturing the spatial location of the vibrating vocal folds in such a motion window across the frames is essential for extracting the kymograms. We extract the kymograms at different cross-sections of the vocal folds for each vocalized segment during running speech. Next, The spatial segmentation is applied to each kymogram using an active contour method to segment the glottal area. The goal of the active contour modeling technique is to extract a specific feature in the image. In this work, the feature we are seeking is the glottal edge. To do so, we have to draw a line or an active contour, also called a snake, close to the edge that we want to detect. The snake is a spline that we can parameterize as a vector. The goal is to minimize the following energy function, which is the summation of an internal energy function, which controls the shape of the snake, and an external energy function that is derived from the image gradient. The snake deforms until it captures the glottal edges. The first step in the active contour modeling is to initialize the snake. The initialized snake should pass through the center of the glottis. For the snake initialization, we use the first moment of inertia that is calculated here. We adjust this moment line to find a more accurate center line for the glottis. The adjustment is based on the gradient information of the kymogram image around the moment line. The solution for the energy function is based on discretization of the energy function as shown using a finite difference method. To extract the snakes, we need to solve the series of equations shown in the bottom of the slide using the dynamic programming approach. Let's move to the results section. The 4 kymograms in this slide are extracted at 4 different vocal fold cross-sections shown on the top image. The kymograms are extracted from the same vocalized segment over 200 frames. You can see the first moment of inertia shown in yellow and the adjusted moment line shown in light blue for each kymogram. After the snake initialization, the active contour modeling approach was applied to the right and left edges of vocal folds. The extracted left edges of the vocal folds can be seen in the kymograms in the left, and the right edges are shown in the kymograms in the right side. After segmenting the vocal fold edges in all kymograms across different cross-sections of the vocal folds, the segmented vocal fold edges are registered back to the HSV frames to calculate the glottal area waveform. The glottal area waveform is computed across frames for each vocalized segment of the rainbow passage. You can see the calculated glottal area waveform for 2 different vocalized segments here. Here is a video that shows the detected edges of the vocal folds along with the calculated glottal area waveform. You can see the HSV frame on the top. The detected edges of left and right vocal folds are plotted on top of each HSV frame in green and yellow colors. In the bottom of the video, the corresponding glottal area waveform is shown, which is synchronized with the HSV sequence. The developed automated snake initialization method accurately located the center line of the glottis in the extracted kymograms. The results show the visibility of the spatial segmentation during the running speech, which provided the analytic description of the vocal fold edges. Also, after registering back the segmented vocal fold edges to the HSV frames, visual inspection showed that the method was able to track the vocal fold edges during vibration. The glottal area waveform was successfully computed using the segmented vocal folds edges during each vocalized segment. The developed automated algorithm for spatial segmentation successfully captured the vocal fold edges across frames, allowing for accurate computation of glottal area waveform. In this study, we analyzed a vocally normal participant. In future, we aim to use the developed method for the analysis of HSV data for larger number of vocally normal participants and patients with spasmodic dysphonia. This will help us to generalize the developed algorithm for norm and disorder and to address inter and intra-subject reliability. HSV-based measures will be developed from the measured glottal area waveform for norm and disorder. Thank you for your attention.